Okay, so this is the last lecture in the course. I decided I would talk about some open questions related to things we've gone over. I've should say I've tried to pick questions which can be stated fairly easily and which you can understand the meaning of them given what we're seeing. Most of them are fairly difficult, and they're not in a form that would be suitable for, say, a PhD thesis. But they're still interesting and they're still important. I'm just warning you that there's, I was more actually one thing in choosing them. One of the things which I could state without a huge amount of preparation, and so that's a criterion. So it rules out some important questions which I could have asked but didn't. And some of these questions are quite old. I'll say a bit about the history as I go on. So the first one is simply: is there a graph with perfect state transfer from two vertices such that the sum of the eigenvalue support of the vertex u and the vertex u is not zero? Now, this is kind of a funny question. Actually, the two oldest questions we had in perfect state transfer is whether there were trees with more than three vertices perfect state transfer. And Gable Coutinho and his colleagues proves that no, the only trees with perfect state transfer are the paths on 2 and 3 vertices fairly recently. So this is sort of some sense the oldest open question. It matters a bit because in all the examples we have, this sum is zero. And in a certain sense, we can see no reason for that. Okay. The other point is we don't have, in a certain sense, we don't have a vast supply of examples of perfect state transfer. We have the things we get from cube-like graphs and things we get by, in some sense, sort of lifting paths. And so if you found examples where the sum was not zero, there would be perfect state transfer of a new type. So that would be interesting. Okay. And so there's a bit of a question that, the eigenvalue support, when you're doing these sorts of calculations, it's nice if you can do them in exact arithmetic. And so in this case you can, because the eigenvalue support consists of the is just a set of zeros, this polynomial. Okay. So the zeros is probably simple, so you can compute this polynomial in exact arithmetic. And the code for computing characteristic polynomials functions on quite large matrices, hundreds of vertices. Whereas the eigenvalue routines are not going to get you that far. So that's the first question. Now, this is okay, I'm taking a graph Y. Make sure I can do this in, and we're adding two new vertices. To A at the vertex A in Y. Now the question is, when is there perfect state transfer between the two new vertices? Now to get perfect state transfer, you need them to be strongly co-spectral, and you can show that there's a necessary condition or necessary and sufficient condition for these two vertices to be strongly co-spectral. But other than that, we know nothing. So it seems unlikely that in general that you're going to get PSD between those two vertices, but I know nothing more than what I just said. I mentioned that you're not going to get your full 50 minutes worth of lecture today, but that's probably not going to worry you. I mentioned that in some sense the biggest class of examples of graphs with perfect state transfer are the things we get from cube-like graphs. You pick your connection set. If the sum of the elements of the connection set is not zero, you've got perfect state transfer. If the sum of the elements in the connection set is zero, you add one new element or you delete one new element, and you've still got perfect state transfer. So perfect state transfer is easy to create on cube-like graphs. Okay, and so I'll ask a concrete question. In a certain sense, we'd like to know how fast we can get it as a function of the number of edges. So the constructions I just mentioned will give you perfect state transfer at time pi on 2. And I have a paper with Chung where we worked out what happens for pi on 4. And at that time, looking at pi and 8 seemed difficult. And I sort of was crossing my fingers and hoping that there would be perfect state transfer at time faster than pi and 4. But Ada found lots of examples and so it can be arbitrarily fast. So one question is, how does the speed compare to the number to the the edge density number valency divided by number of vertices? But the concrete question that's asking here is, can we characterize what happens at time pi and 8? The proof for pi and 4 uses some stuff from coding theory, and that stuff fails when you get to pi and 8. So you need a different idea. Now, this is one question which is getting close to a reasonable question for a thesis. Simone Severini asked, he asked the following: to characterize the cubic graphs, the perfect state transfer. This is again exploring the cubic graphs are interesting because if you're going to use a network, you want it to be sparse. You'd like it to be sparse, and cubic graphs would be amongst those. Severini proved that the 3 cube is the only periodic cubic graph with perfect state transfer. Now, as I said, if you could solve this, you could equivalently ask a question about graphs with maximum valency 3. And I just want to make a comment that a vertex transitive graph with perfect state transfer is necessarily periodic. And so Severini's work determines the vertex transitive cube-like graphs with perfect state transfer. Now, Simone was hoping to determine all the cubic graphs with vertex state transfer, but he was writing this paper up for a conference, and so he didn't have a lot of time. And so he stopped when he had to stop at a certain point. And when he stopped, this is what he had. Okay. But there's lots of questions you could ask. What about the bipartite case? What about the walk regular case? And I was talking to somebody the other day, and they said, what about the 4 regular case? But you can do that. That's going to be 3 case. Cubic case is going to be hard enough. But so that's anyway, that's the question. Now we have various parameters attached to continuous quantum walks, and one of the more interesting ones is the so-called average mixing matrix. Now remember that was sigma, share squared. So it's a nice invariant, even in its own right, but it's also related to the problems. That's a pretty bad circle too. Now we know that the average mixing matrix has got rank 1, and then your graph is K2. Yeah, okay. So the question is, what about rank 2? That's the next step. And now a lot of us put in a fair bit of work into this, and the state of the art is that we, Iriger and Betten came up with a graph on 64 vertices with rank 2. So that's the largest we know. They also have examples on 32 and 16. It's an open question whether you can do more. I was originally thinking that, or sort of maybe I was just hoping that the answer to this question would be no. I'm no longer so confident. And so it's a nice question, but as I said, so a lot, Ada and Harmony and me and Ferdinand and a bunch of other people have worked on this, and we didn't get too far. So it's now we also talked about uniform mixing. Now for uniform mixing, we want the uniform. If we have uniform mixing at time t, then U of t is flat. So it's a flat unitary matrix, or equivalently a complex Hadamard matrix. And complex Hadamard matrices are interests both for combinatorialists and for physicists. I mean, they appear in other places outside quantum walks. So new constructions of new constructions of families of flat unitary matrices are generally interesting. So questions about uniform mixing are interesting. Now the interesting thing is that first question is the only graphs with uniform mixing that are not regular are the complete is the complete bipolar graph K13 and its Cartesian powers. And so the question is are there any other graphs not regular with uniform mixing? I mean, essentially, it's a very natural question. So, I mean, originally we're hoping that if the graph was, if you had uniform mixing, the graph was regular. And then it took us quite a while, and eventually Harmony pointed out to us, well, K13 has uniform mixing and it's not regular. Well, there could be others we don't know. Now, related to uniform mixing, and again to this question about constructing flat unitaries, I'll summarize what we know about cycles in a second, but the question I'm asking, is there uniform mixing on the cycle C9? And if you do that, the next question is C15. Now, C9 is a prime power, and 15 is not, so these could be a little different. Natley Mullen proved that uniform mixing does not occur. That's a really ridiculous type of on the prime cycle when P is at least 7. The case P equals 5 was handled earlier by Tino Tamon and his REU students. And the 3 cycle does emit uniform mixing. Natley proved that apart from C4, no even emits uniform mixing. So uniform, the connection's playing up here. So now we'll have made serious attempts at this. Natley conjectured that C9 did not have uniform mixing, and I wouldn't argue with her. Okay, but no one has any theories about C15, and so it's a I mean, it's not that big a graph, is it? It's only 9 vertices. What makes it complicated? I don't know if I put in here that there's a related concept which I didn't discuss called approximate uniform mixing, so that you get within epsilon of a flat. You can get within epsilon of a flat unitary for whatever epsilon you choose. And so Natley proved that for the prime cycles, you could get this epsilon uniform mixing. And so that means it's very difficult. You can't really do computer experiments and look and see what's happening. The computer experiment will tell you, yes, there is uniform mixing, but it's not. It's just approximate uniform mixing. And Natley had 2 conjectures. If a graph emits uniform mixing at time t, then EVIT is a root of unity. Now, if something like this was true, that would make a lot of things easier. I'll come back to that in a second. She also conjectured that if N's least 5, no connected K-graph is Z of D and emits uniform mixing. Now, I'm a little worried about what happens when N equals 6. Okay, because I can see arguments that say the 6 might be different, but so maybe there should be N greater than 7, but that's Natley's conjecture, so I won't argue. As I said, one of the problems with uniform mixing is that for perfect state transfer, Goebel and I proved there's a polynomial time algorithm, but it's hard to have a graph that has perfect state transfer. So we have a graph, and we want to know if there's perfect state transfer, we can work it out, provided it's not too big, probably. What about uniform mixing? Well, in general, we don't have any such result. And so that makes it difficult for us to get sort of computational evidence in support of any conjectures. So you've got some graph, or for example, the 9 cycle, and we don't really see, we don't know how to move, where to move. And I just mentioned here that Natley's PhD thesis and Harmony's math thesis contained a lot of information about uniform mixing. And Ada has also got papers which I was too lazy to look up at this point. But there's, she was proving you can get uniform mixing on cuboid graphs at short times. The related question here is, well, as I said, cuboid graphs give us a lot of examples of perfect state transfer, and so it's natural to ask which cuboid graphs emit uniform mixing. That's probably too vague a question to be really good. Among the cuboid graphs of perfect state transfer, so that should be a question. You can ask a more precise question. If you've got a cuboid graph with perfect state transfer at some time tau, does it emit uniform mixing at time tau and 2? Now, the canonical example here is the D cube. So it has perfect state transfer at time pi on 2 and has uniform mixing at time pi on 4. And there'll be quotients of the cube which will have similar properties. So some cube-like graphs, there will be cube-like graphs where at half the PST time you get uniform mixing. And I'm pretty confident there'll be some where you don't, but I've not gone and looked. Has anyone got any questions at this point? I'm rattling through this. Okay. So now comes to discrete walks. Now you'll get more information about discrete walks in Harmony's PhD thesis. There's a link on the webpage for the course. And of course, we also have our book, but her PhD thesis is cheaper. So she helped draft the next 3 questions. So now the trouble with the discrete walks, actually there are lots of questions you can ask. And Tina Chen did a PhD thesis on discrete walks. There are lots of questions you can ask, but we don't know as much about continuous discrete walks, and they're harder to work with, and so it's harder to come up with nice, concise questions about discrete walks. But I've got 3. There are one of the problems with discrete walks. Well, okay, we're going to do that. So the first question simply is to find examples of perfect state transfer in 2 reflection walks where the initial state does not lie in the column space of Q. Okay, so the background of this is that Harmony has examples of perfect state transfer where the initial state does lie in the column space of Q. Now, the initial state's a density matrix here, and you get to choose the density matrix. It's not so natural to focus on the vertices in this case. So a natural initial state might be the set of arcs that lie on a given vertex. I mean, well, you can't focus on the vertices because the state space for a discrete walk of this type is the space of functions on the arcs of some graphs. And so, okay, so that's a state space. And so your initial state, well, it could be an arc, but I don't think we have any examples of where there's transfer from one arc to another. But we know almost nothing about that. So it didn't. Then there's a question about uniform mixing. So on the arc reversal walk, if we start at the analog of a vertex state, I defined these guys in the notes. Is there uniform mixing? And the answer is there is for Kn. We don't know any other examples. And also discussed Shan't decomposition walks. And the question then is there an initial state that has uniform average mixing? Now, as I said, there are a lot of questions about discrete walks. It's just that we didn't spend as much time on them, and so we're not as well prepared, so I can't go into more details. And so the last group of questions involves quantum homomorphisms. Now, Gramada and independently Bill Martin and Ada Chan proves that any 2 Hadamard graphs of the same order, or same number of vertices, were quantum isomorphic, and this depended on again on a deep result of Robertson and his colleagues saying that 2 graphs were quantum isomorphic if for any planar graph Z, the number of homomorphisms Z into the first graph is equal to the number of homomorphisms Z into the second graph, which is not quite the most efficient test you would want. In fact, deciding quantum isomorphism is an undecidable problem, but okay, it doesn't mean it's not interesting. But anyway, so now we know that these Hadamard graphs, the same number of vertices, are quantum isomorphic, but we do not have an example of a quantum isomorphism between 2 Hadamard graphs. And that's a little embarrassing. It might be vaguely possible to reverse engineer the proofs of the result on the homomorphism count, but you would. I mean, I'm not asking you to. In fact, I'm not even asking for a result which says, given a pair of Hadamard graphs, here is the quantum isomorphism from one to the other. I am just asking for a pair of Hadamard graphs with a quantum isomorphism. Of course, if you do that, I'm going to ask you the other question next. but we do not have an example of a quantum isomorphism between two Hadamard graphs, and they're all isomorphic. Okay, and the second part is closely related. If I've got a Hadamard graph, give me an example where there's a non-commuting quantum automorphism. Now, the terminology is a bit, I can't think of any polite words to work, but the problem is that we have this idea of a quantum automorphism group. And so it would seem reasonable to say that an element of the quantum automorphism group would be a quantum automorphism. The trouble is that the physicists don't want to count the classical automorphisms, permutations, as quantum automorphisms. So there seems to be a convention that when they use the word quantum isomorphism, they're excluding that case. Now I'm going to be a little more careful. So I'm asking for a non-commuting quantum automorphism. So I want a quantum automorphism where the projections in the automorphism don't all commute. Now, as I said, in general, the usage would be a quantum automorphism. They would normally mean something which does not have all its entries commuting, but I've tried to be a bit more explicit here. And again, we don't have any examples of that. We have very few Schmidt and people have done some work on small graphs about their quantum automorphisms. And so the hypercubes and some radiographs tend to have quantum automorphisms, but there's an awful lot of graphs which have no, for which all the automorphisms are classical. Since we're trying automorphisms, Maria has shown that some of the examples, well, particularly we have two graphs on 24 vertices that are quantum isomorphic but not isomorphic. And Maria has shown that those two graphs are related by what I'm calling local switching. So that's an operation on graphs which preserves the spectrum. And so now the problem is, okay, that's not an automorphism. Okay, it's a similarity. So but we can construct that. Now, the question is whether we can somehow turn a local switching into a quantum automorphism in some cases. I don't believe for a second that all quantum morphisms come from local switching. Although it may be that the examples we know that's true, but I've got no reason to believe that. Part of the reason is that local switching in general it screws up the coherent algebras. So if you have two graphs and local switching from one to the other, the coherent algebras need to be isomorphic. And for quantum isomorphism, we need to preserve that. I said this is likely not a fair question, but just having examples would be, having more examples would be interesting. And this is the last one. Now, when you're working with homomorphisms of graphs, you have this notion of homomorphic equivalence. And so you can break up your graphs into equivalence classes, and then you can deal with the questions equivalence class by equivalence class rather than worrying about individual graphs. And what's nice is you can show that each equivalence class, if you look at the graphs in there with the minimal number of vertices, they're all isomorphic. And so in some sense, there's a unique isomorphism class of minimal elements. And so that graph would be called the core of so you've got a graph X, you've got this homomorphic equivalent graph, which is minimal, that would be called a core of X. Okay, and so you can work with the cores instead of just with working with all graphs. Now it would be nice to be able to do the same thing for quantum homomorphisms, but there's a big problem. We do not we can't tell, in a certain sense, I'm going to use the words wrongly, we can't tell when a quantum homomorphism is surjective. Now that's not quite the right way of putting it, but that's the problem. So you have a quantum homomorphism X to Y. We don't even know what it means to be surjective. Now, there is, in fact, a definition, and I've written it down here. So the jargon is that the quantum homomorphism, what you want is that this condition. So you can cancel on the right. Okay, And so if that holds, then it's epimorphism. And so that is, in a sense, well, if you look at what's happening with the category, this is what the category will give you for the character for a condition. But we don't know. Actually, we don't have an example even where there are non-trivial quantum homomorphisms, and we know, what whether they're onto, whether they're epimorphisms in this notation. Okay. In the classical case, an epimorphism is a surjection, but we're not in the classical case, and everything's a bit messy. And so this is one of the big difference between the category of graphs and homomorphisms and the category of graphs and quantum homomorphisms. Now, it may be that there's not a good answer to it. I mean, there doesn't have to be, but there it is. So this is more an admission of ignorance than a real question in some sense, that you would want something more concrete to actually work on. Any questions? Because that's the last of the open problems.
So if we solve any of these, do we say that we were introduced in this class? That we found this?
Well, that would be kind. There's no reason not to, I guess. As I say, I'm warning you that these are not, most of these problems are not problems I would feed to a PhD student for a thesis problem. I mean, it's nice to have a collection of problems to think about, and and sometimes it takes a long time. I have made up lists like this from time to time, and we have made progress. Okay. But it took us 10 years to come up with a proof that trees on more than 3 vertices don't have 30-state transfer. Okay, and we developed a fair bit of theory in the meanwhile. Okay, but my point is these are open questions, and then anyway, to answer your question, yes, if if somebody poses a question and you solve it or you make major progress on it, then you should cite it. That's kindness. I mean, I don't believe that just because I pose the question that makes me a co-author when you solve it. Although I've met people who seem to think that. So yeah, all I say, it would be nice to acknowledge them, and based on the fields lectures, fields would like acknowledgement, for example. And so yeah.
Well, I would love to find out if anyone of you solved any one of these questions.
Sorry?
I would just like to kind of find out if anyone of the students solved any of these questions.
Well, of course, yeah, we would love to know.
Yes.
Yeah, we would love to be told.
Mhm.
And if you look at the papers, you'll see more questions. I mean, there's lots of places to find problems. You can see the sort of things we're looking at. There are certainly topics related to quantum walks where I didn't discuss pretty good state transfer, and I didn't talk about face vertex walks for discrete walks and things like this. There are a lot of topics that we didn't cover. Now, I'm not overly concerned about it. I was not trying to cover everything in the first place anyway. I'm in no rush, but I wish you all a happy Easter now and lots of chocolate.